All right, welcome to another very exciting episode. That was so exciting just to push the button. Okay, another exciting episode of AP Chemistry here at Spain Park. No, that's okay. Today is Friday, September the 27th, and it is game day. It's hurricane day. It's, hey, let's do some chemistry, and let's figure out these solute to solvent attractions, and how and why do things dissolve in water like they do. Okay? So we will get this mess out of the way so we can focus on chemistry. All right, so we were doing questions 7, 8, and 9 when the bell was ringing yesterday. Okay? So let's just quickly go through these again. So what type of attraction, and hopefully you wrote this down on the side of the problem itself, but what type of attraction, what force do we use, or our energy, to measure the strength of attraction between an ion and water? Coulombic attractions, okay, which is based upon what two things? The charge and its distance, and we measure the distance with ionic radius. I finally heard somebody say it. Now I think maybe I heard it coming from over here too, but ionic radius. Okay, the size of the electron cloud is more for LDFs with covalent substances. For Coulombic attractions, we're going to talk about ionic radius. So which one here is going to have the greatest or strongest ionic Coulombic attraction based on its ionic radius? Why? And again, it's not showing up here, but if I look here, zinc, why? It's the smallest radius. Okay, since D is in the denominator in Coulomb's law, the smaller the number, the greater the delta H. Okay? You can just move it if you need to just get, okay? No, just that handle, just you can move it side to side right there like that. Okay? All right. But you don't really, this is the thing that's most important for you to make sure it's in there. You don't necessarily need to see me, because then I always realize how much I need to go on a diet. But, so I always try and get out of the camera. All right, so then we look at number 8. Okay? Number 8, based on the data above. Now, this one here, I want to really make sure that you guys have. What were the 3 things that needed to be tied together, Jack?
It was like when they keep evaporating into gas, it makes higher pressure.
Okay, so the things that evaporate quickly have the highest vapor pressure. So what does that mean about the attractive forces? The weak. Higher the vapor pressure, the weaker the attractive force, the lower the boiling point. Okay? I'm stressing that, aren't I? That means I'm saying it with bold print letters. That means
No, for the test.
it's very important. Okay? It's probably not oh my information. It's probably very testable information. Okay? And then lastly, when we look at number 9, which of the following helps to explain why the value of delta H for the dissolving of calcium fluoride is positive? How do we know it's not A? Calcium fluoride is insoluble in water.
Because it is.
Okay, everything has attraction, but what else? Okay, it's a positive heat solution, so it dissolves. If it didn't dissolve, well, if it doesn't dissolve, what would the delta H be? 0. Because nothing happened. There's no reaction. There's not going to be any gain or loss of heat because nothing happened. There's no attractions. There's no breaking apart, requiring energy. There's no coming together, releasing energy. Nothing. It'd just be 0. Okay. How does calcium fluoride dissolve? Does it dissolve as CaF2 particles or molecules? They dissociate as ions, right? So, and again, sometimes the wrong answers can help us to understand better why the right answer is right, and make sure that we understand things. That's why I want to go over that. So then again, in our equation, Now bring it back over here. We have delta H of solution is equal to delta H1 plus delta H2 plus delta H3, okay? This one is always positive, this one is always negative. This one's positive as well, okay? That's fine. This one's positive as well, but the breaking apart of the solvent generally doesn't require that much energy, so it's not as significant. So we're really gonna focus on these two, okay? So which one of these, calcium ions have very strong ion-to-ion interactions with fluoride ions in the crystal lattice. Which one of these values is it referring to? Delta H1, 2, or 3? 1, which is always positive. What about calcium ions have very strong ion-to-dipole interactions with water molecules?
H3.
That's your delta H3, right? This is your solute to solute, and since it's ionic, it's talking about the lattice energy. This is your energy of hydration. This is the water attaching to the solute particles. That's that ion to dipole attraction. In this case, the energy of hydration. This one's always negative, this one's always positive. Okay? This is another really important concept to know which one is going to be greater. So if the question said, if they did this and said that this is negative, well, first off, what's the answer then to this question number 9? C, because this is the positive one. Obviously, this one has to be greater than that one for the delta H3 positive. Right? Now, on this one, if I said this, if I said negative instead of positive here, then this one's going to be greater, correct? Do y'all see that? Great multiple choice questions. Great multiple choice questions. Are you catching my drift? That this might be a great multiple choice question.
I was on the test.
Third time's a charm.
So, you said H1 was always positive,
Yes.
right? Is H3 always negative?
Yes. Bonds breaking always requires energy.
Okay.
Bonds forming always releases energy. Don't always get to say always. Always. Just letting this just kind of rest a little bit. Let it just kind of sink in a little bit.
What is H2 the one that changes?
H2 is positive always, but that's the solvent, and it only has to kind of stretch a little bit. It doesn't have to really break completely apart like the others do. All right, so now, let's take a second and look at number 10. Okay, you get 90 seconds. 90 seconds. So that's 60. Hopefully, as time goes on, this is going to be faster. This is going to be a 30-second question, not a 90-second question when we look at this. First off, AgNO3. Is that an ionic or a covalent compound? Ionic, so it's gonna dissolve as ions, not as molecules. So we know it has to dissociate, okay? Notice again that water is always represented by Mickey Mouse, okay? So, what's the answer?
A.
A. Why A, Carter?
Because the negative part of water is with the Ag and the positive part is with the
Okay, the positive end, water is a dipole, it's two poles, it's a polar molecule. So notice, and this is super important if it's a free response question and you have to draw it. Notice there's no label of what oxygen is and what hydrogen is. It's understood that water is H2O, that you as a AP chemistry student know that water is H2O. However, I will say that in the past, many times, I get the books back and students put water as O2H. Okay, yes, they just freak out. I don't know how that happens, but they draw two oxygens and one hydrogen. Okay, and I just want to I get overwhelmed. I want to throw up. Jack.
I thought it said like before the reaction occurs, so that means like AgNO3 would.
Before, no, there's a, which of the following are best side, before there, this is probably relating as part of a different reaction that silver nitrate is going to be in, but silver nitrate in water. Okay, it's just before, what best represents, and what's the key? AgNO3 solution. Okay, the solution. Before it reacts with anything else, and so that's probably part of a different question. They just kind of made this into what, this is often a free response question, and this is what I'm trying to point out. In the free response question, you always represent water as Mickey Mouse. You do not put oxygen and hydrogen, don't label it. You know it's H2O. For sure, don't label with charges, positive and negative. Even if you use the little delta sign for partial positive, partial negative, don't worry about that. All they want to see is the orientation. All they want to see is that the oxygen, the negative, that you know the oxygen is the negative portion of the water molecule, that it's polar, and that's the negative side. Okay, and that is going to be attached, and it's going to be attracted to the silver, the positive, and then the positive side of the water is going to be attracted to the negative.
Okay, so since it's a solution, do you have to draw the other water molecules?
No, no, generally not. They just kind of putting that in there. Most of the time, they will say just using one formula unit. Remember, a formula unit is an ionic molecule. So when it says one formula unit, that means one AgNO3, one molecule. But ionic compounds don't form molecules, therefore we don't call it a molecule, we call it a formula unit. But you just use one, and then they said use at least 10 water molecules, or sometimes they say using 4, they'll tell you how many water molecules to use at the most. But you just need to be surrounding it. Now, I generally make them actually touch, okay? But they're showing here, so as long as you get them oriented in the right way, then you're going to do it right. So many times they make you draw this out somehow, some way, and I can't express enough to don't try to be too descriptive. Don't try to overdo it and say this is the oxygen, this is the hydrogen, this is the negative, this is the positive. You don't have to do any of that. All you do is show Mickey Mouse pointing one way or the other. Okay? All right. Go to the next page. Let's look at this question. I'm going to give you 30 seconds on this one because we haven't really talked about this one. Alright, make a guess. Now the reality is that we hadn't talked about this, but you should be able to narrow it down to a 50-50 guess. Okay? Nonane and 2,3,4-trifluoropentane have almost identical molar masses. What does that imply? And that's important when you see that, because questions say that all the time.
Mr. Roberts, this is not the
We
question.
skipped a page. Is this, did you?
So I did the wrong question.
It's on the other page.
Well, I just put this one up. Why didn't you do this one?
You said the next one.
Well,
That's-
well,
I did exactly what they did in our
Yeah,
book,
I
but
did- I
I
did
realized
that
I did the
too.
wrong question. So I
do
did-
this one.
You're getting fired, it's on video.
Mine aren't stapled. Do this one. The one that I put up on the board. All right. Again, we're just gonna kind of make a guess. We hadn't really even talked a lot about this as far as especially the choices. But again, when I'm looking at this and it says that they have almost identical molar masses, what does that tell you indirectly?
Same size.
Okay? So what's the same size?
Electron.
The electron cloud. So LDFs should be about the same, but they're saying that they're not. The boiling points are different. Okay? The 2,3,4-trifluoropentane has a lower boiling point than the nonane. But when a molecule, a covalent substance, boils, what bonds break? The covalent bonds within the molecule, or the IMFs between the molecules? IMFs between the molecules. So what two answers can we immediately eliminate? The CF bond is easier to break than the CH bond? Are we gonna break the covalent bonds within the molecule when we boil it? No, this is a inert. We're not gonna break these bonds. You're always gonna break IMFs, bonds between molecules. So you have to be, your answer has to deal with IMFs, not covalent bonds. Whenever a covalent compound boils or melts, you're breaking IMFs, not covalent bonds. Whenever your covalent compound is boiling, you're breaking IMFs, not covalent bonds. Okay? Are you with me? I feel like you're with me.
You want to write it
I
down?
feel like you're
Right now.
distracted.
Mr. Roberts, that's not what?
I feel
Not
like
covalent,
there's something in your lap. Let me say it louder.
Louder.
If
If.
a covalent compound is boiling, you are breaking IMFs, not covalent bonds. Did you say it's soft?
Some on the test.
When you're breaking molecules apart from one another, a covalent substance is boiling. You're breaking IMFs. You are not breaking covalent bonds. Say it loud, say it soft. It's the same thing. All right. Is that important?
Yes,
Yes.
probably.
Definitely. So, the CF bond is easier to break. So I can immediately discount that because I'm not breaking bonds. The CF bond is more polar than the CH bond. Now, it is more polar. Okay? So what does that mean then that in terms of intermolecular forces?
Stronger.
Well, what does it have if it's got a polar bond?
A positive negative.
Dipole.
Dipole. Okay, we're talking about IMFs. Dipole. But does that jive with the data? No. So that's not going to be an explanation as to why nonane has a higher boiling point, because it's more polar, dipole, but that would imply that, you know, if we just followed logic, it would say that that's going to be a higher boiling point, but it's not. So we can get rid of that one. But the carbon chains are longer in nonane than they are, and the carbon chains are farther apart in a sample of nonane than they are in 2,3,4 trichloropentane. Now, we had really talked about this part of LDFs, but the longer hydrocarbon chain gives more surface area for the two molecules to combine together. Okay? So as a result, that's why it's going to have a higher boiling point, because it's got more surface area for the two molecules to stick together, or for nonane molecules to stick together. Okay? It's a longer chain. Okay? The carbon chains are farther apart in nonane than they are if they were farther apart. What do we know about attractive forces? The farther apart, is the attractive force going to get stronger or weaker? Weaker. If the molecules are farther apart, they're not going to be attracted as strongly to one another. It's the longer chain gets more surface area. So here's a variation of the question. If they gave you a straight chain hydrocarbon versus a bent, okay, something that looked carbon, a straight chain carbon, something like that, versus something that looked like this, with hydrogens all around it. This is going to, even though they're going to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, they're going to be nearly the same molar mass. This is going to have more surface area than this. This is going to have higher London forces than that. Okay, it's a surface area thing. Okay?
More
Say that
surface
again.
area means higher boiling.
That's right. The LDFs have more places to stick together, so they're going to have stronger LDFs. So higher boiling point, yes.
The one below, is that gonna have greater LDFs?
No, this one is.
Okay.
Now, they both have 5 carbons, and they'll have the same amount of hydrogens all around it. They got hydrogen, 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 okay, all the way around. Okay, but since this is linear, it's going to have more surface area. It's going to make it easier for the molecules to stick together than like this.
But
So-
like, shouldn't the electron cloud be like circular because of?
Well, it's going to be here versus.
Oh,
Yeah.
okay.
Okay. All right, which one did you guys do next? Go first.
I didn't do it.
This one?
Yeah.
Yeah.
No, the one before.
This one?
Yes.
That one?
Yes.
Okay, this one. This is a good one. You get 90 seconds on this one for sure. How close can you guys get over there? Where are Tate and Calvin again?
Calvin is at a wedding.
Oh, that's right. And Tate is
He's
at
sick.
some school related something.
No, he's sick.
Oh, he's sick?
Yeah.
Oh, I thought he said he wanted to get. I knew Calvin was. Okay. When again you have particulate diagrams, the best thing to do is to count. Now, how many of y'all think the answer is A? How many think the answer is B? How many think the answer is C? How many think the answer is D? How many don't think? Okay. All right, now look. The first thing I'm going to do is I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nitrates. Okay? But I'm also going to come over here and I'm going to count magnesiums, or my positives. 1, 2, 3, 4, 5 magnesiums. Okay? Now, the magnesiums, the nitrate is going from a 1 to a 2. That's going to make things complicated. More complicated as far as trying to figure stuff out. But the magnesium is going from magnesium chloride, again, spectator ion to spectator ion. They all have to be accounted for, okay? So my magnesium here is, if I give a chance of magnesium, if it's 2 molar here, okay? Now it's 1, 2, 3, 4, 5. But I'm going from 5 in 1 liter to 5 in 2 liters. So what's happening to my concentration of my magnesium? By how much? Half, right? I'm going from 5 in 1 liter to 5 in 2 liters. They didn't change at all. My magnesiums didn't change at all. You just following me on that? You have 5 magnesiums here, they're spectator ions, 5 magnesiums there. The 5 magnesiums here are in 1 liter, the 5 magnesiums here are in 2 liters. So what happened to my concentration of the magnesium? It's half. So do I have any in here where the magnesium went to 2 to 4? That's double. The magnesium stayed the same here, 2 molar to 2 molar magnesium. Okay? Here it went 1 molar to 1 molar, stayed the same. But on this one, it went 1 molar to 0.5 molar. That's the only one that it could be. And you just count. Now, I could have counted this one. I have 10 here. I still have 10 there. But, okay, 10 in 1 liter to 10 in 2 liters. Okay, but my magnesium, okay, nitrate, I have 10 in 1, so it's going to go to, again, it's going to go half to what it was before. But again, it's more complicated because it's the 2, and so you got to account for that too. But if you just count the magnesiums, the thing that's 1 in 1, you can just do it just like that. Okay? Whenever you have particulate diagrams, just count. It's a good job for those of you that got that one. That one's, I consider that one to be pretty hard, just from a visual standpoint, trying to go through and see that. Count the magnesium. Count the thing that's only the 1. If you know, if that was the only one where the magnesium halved, you didn't have to worry about the nitrate. All right, let's pick another one to do. Let's pick this boiling point one. "90 seconds, go." answers?
No.
Got 10 seconds. Okay, again, now just test taking, if you got to a problem like this and you just really are clueless, you gotta skip that one. Circle it somehow, make a notation, and then you gotta come back to it. Run out of time on the ones that you're unsure about. Make sure you get to all the multiple choice questions that you at least have a chance at answering correctly. Don't run out of time on the last 5 or 6 when maybe you're gonna know the answer to those. You haven't had a chance to look at them because you spent 4 or 5 minutes on one question that you weren't really quite sure about. Okay? So 90 seconds is the maximum you should spend on any one particular question. Hopefully you get more other ones you can pick up faster than that, and you can make up some time to be able to go back and check, okay? But, all right, so now let's talk about thought process. First thing first, when you look at this problem, immediately what type of compounds is this all talking about? Ionic. Does everybody see that? The minute that you're looking at this problem, it's dealing with ionic compounds. All right? Because it's NaF, MgO, and then they're talking about NaCl. All 3 ionic compounds. So what 3 things are tied? Well, what other 2 things are tied to ionic? Coulomb's law, lattice energy. Those things just ding, 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 ding in your head. Okay? Got to. Because you have to know which file, how to attack that. If you know that is Coulomb's law, then we look at product of the charges over ionic radius. Well, what's the product of the charge here? +1 -1, +2 -2, and then NaCl is +1 -1. So which one do I know automatically is the greatest? MgO. So I know NaCl is going to be less than this one. Just immediately, just looking at it like that. So I've only spent 10-15 seconds so far. Okay? And now I have to compare NaF to NaCl. So what's the deal with my product of my charges? They're the same. So now what do I look at? The ionic radius. So I have Na, I'm going to compare I'm going to compare Cl minus to F minus. If I want to know if it's greater, okay, which one's going to be greater, the smaller or the larger? Smaller. The smaller one's going to be larger. So the F minus, the NaF, is going to be a stronger lattice energy, greater lattice energy than the NaCl. So what does that mean about the melting point of NaCl?
It's gonna be lower.
It's going to be lower. So it's going to go NaCl, and then NaF, and then MgO. Okay? So NaCl will have a lower boiling point than NaF because the Coulombic attractions are weaker.
That's what
Okay.
we're talking about.
Do what? Hey, ionic,
It's 6 on 6 ends.
ionic, Coulomb's law, lattice energy. Those 3 tied together. We don't need to worry anything about IMFs here. IMFs only apply to covalent. When we're in covalent, we don't worry about lattice energy. Okay? We got to get in the right system, the right file in our brain. And I'm trying to help you to connect the words. Okay? Because you know the right answer, you just got to get into the right file. And you just got to make those connections. I'm teaching you how to work your own brain. Okay. Last one on this. You can put in, don't X through the whole problem, but you are not responsible for number 60 on this. Okay? We're going to do number 59. Okay? We don't know how to do number 60 yet. We're going to learn how to do number 60, so you don't want to necessarily scratch all the way through it, but we don't know how to do it yet. No. It's equilibrium and Dalton's law.
What does the PM stand for?
What does the PM? That's picometers. That's just a measure of length. Alright, this should be a 1-minute question. The figure above shows that in solid hydrogen fluoride, there are two different distances, and that's kind of a clue that that's a distance measurement, of hydrogen and fluorine atoms. Which of the following best accounts for these different distances? So we got this one and this one. Now, before I even read any of this, what type of bond is this right here? That's a covalent. What type of bond is the dotted line? Hydrogen bonds. Covalent bond, IMF. Intermolecular forces. Okay? So accommodations necessary of bond angles. Again, as soon as I see covalent bond, hydrogen bonds, it's got to be something related to that. The difference in strength between covalent bonds and intermolecular attractions. I like that answer, but I'm going to read them all.
No.
Different isotopes of fluorine. What's it?
What is the, like, which one is an intra?
This is the intra. Okay, that's the covalent bonds are within a molecule. Hydrogen bonds, IMFs, are between the molecules. So here's a molecule, here's a molecule. This is the bond between the molecules. Okay? What are isotopes? Again, understanding what the wrong answer is talking about helps us to understand better. What are isotopes?
Same
Same
element, different
element,
neutron.
Different neutrons in the nucleus. Does the size of the nucleus affect the size of the atom at all?
No.
No, it's not going to affect anything. So isotope, that's just kind of really just random, thrown in words that you don't know, well, that just, you know, maybe somebody wouldn't know, you know them, okay? So this is just, isotopes are in the nucleus, doesn't affect anything. Uneven repulsions among non-bonding electron pairs, okay? Well, are there going to be repulsions here? No, those are attractions, okay? So, accommodation necessary bond angles in the formation of the solid. If it was going to do that, they'd all kind of be equal bond angles. But that's just kind of another random, just kind of statement. But again, we're talking covalent bond, intermolecular bond. B is the only one that really makes sense. Is our confidence level going up at all?
Yes.
Last two right.
You
Okay.
can
Yeah, I
test
can
right
say
now.
the last
You can
two
test
right.
right now, dude.
Okay.
I'm joking. Just him. Just him.
Yeah, he just wants it out there. Oh, we do have a test Monday.
Yeah. Are you stupid?
But wait, there's more.
Oh, yay.
Nope,
I was
here you go,
hoping to
let's
give
do it.
I don't even like it anymore. I don't even like it.
No, you're not putting it I love you.
I'm gonna wear a shirt. I
We get to use our academic opportunities to prove this.
Okay.
I'm gonna use my academic opportunity to.
Come on, you're on camera.
Oh.
The entire world is going to hear it.
All 20 of your viewers.
What is this?
All right.
What? That's a good thing? No, I said.
We're gonna
it
skip-
feels like a tomato.
We're gonna skip. Look, we're gonna skip the 15 because you need the picture and everything. And I'm gonna ask number 15 in a different way. Okay, I'm gonna ask number 15F right here. C2. I'm gonna say this: C2H4 is only sparingly soluble in water, whereas C2H5OH is 100% miscible in the water. 100% soluble. Miscible means you can mix them in any ratio. Okay? Why would the C2H4 only be partially soluble, sparingly soluble, whereas the C2H5OH is completely soluble? Okay? Yeah. Don't, again, the formula kind of gives you the clue.
Oh, we're doing that.
You're just doing that, but I totally reworded it. Why is C2H4 only sparingly soluble in water, while C2H5OH is completely soluble in the water? Okay, well, it's just, I want your right answer. as you can see, these are right off old AP tests. Doing the Lewis dot structure and E, we're gonna memorize, that part's easy. I think the way they worded F was very abstract and I didn't like it, okay? But I don't get to write the test. All right, who can answer this? Who wants to answer? Go ahead, Jack.
C2H5OH forms more hydrogen bonds with water than C2H4, which makes it more soluble.
Okay? I would say that that is probably half right. The C2H5OH can form hydrogen bonds with water, which gives it strong solute to solvent attractions. What about the C2H4? Sam, go ahead and answer the rest of that.
It only has dipole-induced dipole forces, which are very weak,
Okay? Consequently,
meaning that it's not soluble because it doesn't want to break apart H2O and
okay, so the dipole-induced dipoles are too weak.
To overcome the bonds
What type between water?
Bonds.
What are the intermolecular forces between water? Water molecules. Hydrogen bonds. To overcome the much stronger hydrogen bonds. Y'all, in your notes, this is under that, the solute to solvent. This is, I think, response C in your notes on why nonpolar doesn't dissolve in polar. That's the one I've told you, you need to learn those 4 responses almost verbatim. When you're studying, you need to know those. So when you go to your notes, here's the answer. When you go to your notes, here. Okay, let me finish this thought, I'm gonna give you a break.
What did you say?
Okay?
Yeah, I know.
All right, so here, look. Here's the solubility rule. Like dissolves like. Okay? Now look, let me just finish this thought. Like dissolves like. When you're trying to explain why some things are soluble and other things are not, there's 4 responses that are the answer to any possible combination of this, that you just need to know these almost verbatim. Okay? This is huge to study for Monday. If it's compounds such as a salt, like NaCl, we're going to have the strong ion to dipole attraction, which, allows the negative part of the water to be attracted to the cation, the positive part of the water to attract to the anion. This is called ion dipole. This is a very strong solute to solvent attraction, which causes it to be very soluble. Same thing on polar. It's positive attracts negative, positive attracts negative. But then you go to this part C, right here. This is the answer to the C2H4. Okay? Well, not that. Not that. Not that. Where is it? Dog on it. Where is it? Yeah. Here it is. They got out of order. Okay? If a nonpolar is mixed with a polar, there are only weak London forces or dipole-induced dipole forces that are not strong enough to overcome the much stronger dipole-dipole and or hydrogen bonds between water molecules. Therefore, the water doesn't separate and the solute, the C2H4, does not dissolve.
So what's the difference between, like, the induced part of it and just dipole-dipole?
Dipole-dipole is permanent. It's a permanent polar, positive, negative end, whereas induced is just a temporary polarization, and then it goes back to normal, so it's much weaker, because it's not permanent.
How the induced one is different.
Polar versus nonpolar. Hydrocarbons are nonpolar, they only have induced dipole. C2H4 is totally nonpolar because it's a hydrocarbon.
Okay.
So it only has the induced dipole. Water's polar, so it's got dipole-dipole and hydrogen bonds. If it's got phone call, it's gonna be dipole-dipole.
So wait, the dipole-induced dipole is temporary and weak?
Yes. Okay, so this is the answer, and you can kind of shorten it up a little bit, but be specific. Instead of saying solvent, you say water. Okay, and so you, instead of saying the non-polar, you say C2H4, but you just plug in here, the C2H4 only has weak induced dipole attractions with the water, which are not strong enough to overcome the much stronger hydrogen bonds between the water molecules. Therefore, the water molecules do not separate and the C2H4 does not dissolve. Okay? That's the answer to any non-polar substance not dissolving in water. And the A and B are answers to why ionic and polar do dissolve in water. And D is why non-polar dissolves in non-polar. Those are your answers to the free response questions. And I hate to just say memorize, but hopefully we've done it enough to where they're starting to at least become part of your long-term memory and you can kind of pull it out. Okay? All right, let's take a 5-minute break and we're going to come back and do a lot more of these. Those of you watching around the world on this exciting video on YouTube, you can fast forward the next 5 minutes.
So slide where it gets ad revenue.
There were times when there were times
Welcome
when
to the free shout out,
this can
man.
be what, infer or something? Because there are times when this can be written this.
Are you gone?
Yes, sir.
So
All right.
if you say.
So you only need 20 minutes worth, but we're just going to keep going over some of those problems. The biggest thing is to know which ones we go over. We're not going to do them all.
They could be stronger if there's more of them. The hydrogen bond overrules everything in like the context where they're like the same size.
So the same amount.
Same electron. That's like in this question earlier, when we were saying like the surface area. So if this greatest surface area, you could say that.
When is this video sponsored by?
Only
Sponsored.
This is sponsored by the SPHS bowling team, which, by the way, needs some help. If anybody wants to join our calendar fundraiser, pick a date on the calendar. If you pick the 2nd, you can bring me $2. If you bring the 15th, you can bring me $15. I need to fill a calendar. Or you can pick first. But 0 is not a date.
So if I pick the 31st of the previous month, does that mean you give me $1?
If I donate, do I get anything in return?
You get to feel good about yourself and know that you helped possibly support the next state champion Spain Park High School bowling team.
Nah. I'll actually consider.
I literally just found it on TikTok.
I've had 2 students participate.
How did you know that? You told me. No.
Hey ladies, just for the record, the video is still going.
I'm talking about.
I know, I'm just saying, before you divulge any personal secrets, I don't edit. Okay. Remember my dilemma from yesterday? Should it stay or should it go? Let's see if I can get
Yeah, me too. Oh, the one that's fluffy, the one you said. Sure, that means
Okay.
Does this look good to you? Because the land is how was it leaving the NPS thing? And then you cover it in pancake batter. Okay, if I'm like hungry enough, if I'm hungry enough, it's really good. And with a chocolate chip. Does that one 2 on it?
You should be happy at the 17.
Bro, what? Where'd you go to the vocab quiz?
I got a-
brain deleted. Okay, like some
I
days
got a
are
50
just
second
like that.
vocab.
Nope.
I figured out we had our work that test so
Y'all
confident.
aren't on it.
I'm gonna get vocab,
Y'all aren't
but
about
I'm gonna
that
just do
way.
the thing. I
I don't think I made an A in total on the test. Seriously. I don't think my net total was an
And you know, he was hard too.
A. No, on Hughes, I think I made a C. I was so bad. It was just bad. Yeah,
You realize that you're still on your recorded, right?
who cares? We're talking about academics.
But they're skipping 5 minutes.
Who's gonna actually see me?
Most everybody's watching on 1.5 or 2 times.
I didn't watch his dead
If you ever posted a video, I just wouldn't watch it. It has like half the questions on the test, okay? But the other half, they're nowhere to be found.
They're nowhere to be found.
Somewhere.
She definitely pulled up the text. But like,
No, not even the notes, it's just perfect notes. Every single thing I fell out of it. Every single one. I studied overall, and I did zero. I was like,
I don't think this is the last test before the 90s. So like our grades are good.
I have an 84. I just need to keep a B. I want her class. Her class. The reason why I don't have an A is because I failed
no,
that.
you can still have the Australia essay.
Oh yeah. No, but I failed that. What was that thing? That first map that we ever did, I failed that, and that's why I have. That's what I failed. Yeah.
No, but she said that she might not be able to Australia. That might be for the next.
Then I'll start off with. Her essays aren't even hard. Miss Love's essay though.
Sadie yesterday, and then y'all are trying to crack.
I said, yeah, I don't eat greens. Kevin said, I can tell. Oh, I can tell. I said, hey Kevin, there you go, talk to that video later.
And then it's
There was one second to pick it up.
I had to sacrifice my AP3 calc test to study for huge and
I sacrificed love test to study for
everything is getting sacrificed for love I have. I will sacrifice, and like maybe not just classes.
Yeah, I feel like this class, I should study the most.
No, because like
I mean, yeah, I feel like this class deserves the most.
Because like this is like my top priority. Everything else.
This is my top priority. You know, I have the exact 80. So I need
I have
to
92, but if I don't go to the next step, I need to go.
But again, the B is an A.
But then the C and the D.
But an A is like a super A.
Yeah. Okay, here we go.
Oh.
Here we go.
You sure you don't want to eat no more bites in your sandwich?
Yeah, come on, you get half of it.
It'll wait. Here we go.
It's gonna get cold.
Here we go.
Colder.
Sandwich will wait, the clock won't. Welcome back, everybody.
What are we streaming today on the channel?
We should do food reviews.
Today we have photons.
Yes, I know. Oh my god.
We got Mad Rock beer.
We found that there's a Pringles somewhere down there.
No. Pringles don't last that long.
Ah.
Okay.
I love Pringles.
I'll eat two. I'll eat the whole can in one sitting.
I don't eat a Pringles.
That's how I keep my
I
dad
can't get
on.
my hand down there. That's not a dad about, that's like a...
Come on. Alright, here we go. Let's look at number 4A. 4A. Follow me. Who wants to answer?
A or B? Both?
Just A.
Oh, just
You only have to do A.
okay.
Anybody? Go ahead.
The boiling point of CS2 is greater than that of COS because it exhibits stronger dipole-induced dipole attractions than the combined forces of dipole-dipole and dispersion forces of COS.
Okay?
Wow, that is such a.
Where do you write that? Like,
Well, you know, you're allowed to maybe write on the other side, or maybe pull out a different piece of paper, or, you know, figure out, because it's really, in this year, they had the question, and then they had like 4 or 5 lines, you know, like 2 pages of lines that you would put your answers in. Then around 2021, somewhere in that range, they finally started putting the lines underneath each question, rather than just having all the questions and then having 2 or 3 pages of lines, because everybody would try and squeeze them in here. So, read the first part of yours again.
The boiling point is greater because it exhibits stronger dipole-induced dipole attractions.
Okay, where are the dipole attractions coming from? Is it being attracted to water when it boils? What's it being attracted to when in boiling? Itself. So would this be a polar or a non-polar molecule? Non-polar. 2 ways that we're going to know how it's non-polar. What's number 1? The one that you guys know. No phone call. Okay? Carbon and sulfur are very close in electronegativity. Now, you're not expected to know that. But if, just for the record, it's 2.55 is carbons, 2.58 is sulfurs. So there's only a difference of 0.03. So they're almost exactly the same. Now, once we get into bonding again and we look at the structure, we're going to see that it's drawn, it's linear. We're going to learn everything there is to know about CO2. Okay? But sulfur's in the same family as oxygen, so CS2 is going to have the exact same structure as CO2. Linear. Which means that even if there was, it's going to pull that way and pull that way, if it's symmetrical, it's for sure going to be nonpolar.
you said non-polar is polar.
Yeah, polar. Those are the 4 most electronegative elements. They're the ones that do not share electrons well. They hog them. So this is nonpolar. So what's the only type of attractive force between these 2?
LDFs.
LDFs. You can say induced dipole, or LDFs. Okay? So it's induced and induced. Okay, so it's just non-polar. Okay? But again, this is the type of question where they're trying to trick you, because now this one has oxygen. So that makes it have a polar end, right? So what type of attractive forces are there between the COS molecules? So, jury say it, since you don't normally talk?
LDFs and dipole.
Okay, you got LDS. So the second part of your statement was 100% correct. Okay, and the rest of it is just the only attractive force with the CS2 are induced dipole. Okay, or LDFs. Either way you want to say it. Yes, sir.
So what's the complete answer?
Okay, well, let me say a thought, then we'll say it out. Okay?
Wait, why is COS dipole?
Okay, because the oxygen over here, anything that has phone call in it, fluorine, oxygen, nitrogen, or chlorine, we're going to call polar bonds.
Yeah. Oh, and then if it's connected to a hydrogen, does that mean it's a hydrogen?
If there's a hydrogen attached to a fluorine, oxygen, or nitrogen, then we're going to call it hydrogen bonds.
Okay.
On the AP exams, if you don't specify what type of LDF it is, do they take off, or do you always just write London dispersion force?
Well, you can just say LDFs, but I mean,
Well, I mean, I'm not saying like the abbreviation, but I'm
Yeah.
saying like instead of writing, or dipole and induced dipole, you just write.
yeah, I think that they're going to give you credit for both, either one. They're synonymous with one another. Okay? All right, so, but here's the deal. This is polar. This is dipole, and LDFs. So in our minds, if we didn't have this, if I just looked at this, I'm going to want to say it's got dipole, and London forces, therefore it should be stronger than just London forces. But data rules. Data dominates. this has a higher boiling point. What does that tell me about the strength of the attractive force? It's the greater than this one. So, why are these LDFs so much stronger than these LDFs?
Because there's a bigger electron cloud.
Bigger electron cloud. Sulfur is much bigger than the oxygen. So, CS2 is much larger than COS, therefore its LDFs between molecules are greater than the combined London forces and dipole-dipole interactions between the COS. As a result, it takes more energy to break those molecules apart from one another, and it has a higher boiling point. Where'd you get lost at the beginning?
So with LDFs, it's like the bigger the electron cloud, like the bigger the radius,
Yes.
that makes it a bigger boiling.
Yes.
But then if you have like the lattice energy stuff.
Well, lattice, yeah, it's opposite.
It's the opposite.
Yeah, because it's a completely different force. All right, so CS2, there's so many different ways you can say this. CS2 has London forces between its molecules, whereas COS has London forces and dipole-dipole. However, because the CS2 is so much has a much larger electron cloud, its LDFs are stronger than the combined London LDFs and dipole-dipole of COS. Biggest thing, name the forces, name the fact that the LDFs of this one must be greater than the combined LDFs dipole-dipole of COS. As a result, it takes more energy to break the molecules apart from one another. Don't just say break the molecules apart, because that makes it sound like you're decomposing it. Make the molecules apart from one another, thus it has a higher boiling point. Carter, did you get all that? You
Yes,
weren't
sir.
writing any. You weren't writing any of it. You do have it? Okay. Now, does anybody want to look at B?
No.
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 Well, just not solve it. Just tell me how you'd solve it.
Isn't that like that?
I would
P1,
skip it to save time on the
I
exam.
know. Hey, the reality is that you're gonna pray for a problem like this, because this is an easy money problem question. We just hadn't reviewed it yet. But what are you gonna say?
That P1, B1,
No, but you're in the right ballpark.
or is that ideal gas law?
The ideal gas law, PV equals
And
nRT.
NV.
Anytime, I'll just tell you this, anytime you see a gas with a pressure, volume, and temperature or anything, it's PV equals nRT, every time.
I was just pervert.
Kim nerd.
You just,
You're on
On
camera.
camera.
okay?
Oh, we're getting demonetized.
I know.
Oh, no.
I'm gonna get kicked off of YouTube because of you.
Wait, you said the way you saw B was,
PV equals nRT. Now you gotta change grams to moles and then plug it into PV equals nRT. But again, we'll come back to that when we get to gas laws at the end of the semester. All right. Let's look at D now. D1 and 2. And I'll just say this, when it says identify, do you have to write anything other than, no, just identify the forces.
you said D, right?
D1 and 2. Okay, you got 40 seconds. So we're running out of time. Alright, so D1, in unison, what are the types of intermolecular forces in HCl? LDS, dipole-dipole. How do you know it's dipole-dipole? Phone call, CL's polar, phone call, okay? Are there hydrogen bonds? Because only phone, okay? So we're just getting that, if I say it enough times, we say it enough times, then it's gonna be permanently in there, okay? Now, this kind of does things from the opposite direction. Which is gonna have the stronger attractive force, CCl4 or HCl, and how do you know? Okay, you've answered a bunch, I'm trying to let somebody else. But I'll come back to you in a second if no one else volunteers.
You know that I know.
Which one has stronger attractive forces, CCl4 or HCl?
I got this one. So CCl4 is going to have stronger attraction forces because its electron cloud will be bigger. Saying that both of them are going to be polar. The increased London dispersional forces of CCl4 will lead it to being stronger.
Okay. What data, what evidence says based on the information above, what above tells you?
HCl remains a gas at 70 degrees and CCl4 condenses.
So what does that tell you?
So that means that HCl is weaker because it stays a gas and doesn't want to combine together.
Okay, let's say it in terms of the other one then. The CCl4 is
CCl4 is stronger because it wants to bond.
because it condenses at the lower temperature.
So I'm right.
Yes.
Dude, no way.
Wait, where did you
Way.
find that?
Way.
It's in like the paragraph above.
Oh,
Okay.
Where?
Okay.
I'm
CCl4
taking this class. Can I
condenses.
get this and put it on my
Okay.
transcript?
CCl4 condenses while HCl remains the same at 70 degrees. So it's kind of, remember, the condensation temperature is the same as the boiling point. So if it condenses at a lower temperature, okay, so it's at 70, but HCl is still a gas, so in other words, it's going to be more sticky than the HCl. So as you're cooling it down, cooling it down, cooling it down, it sticks together, so technically it's got a higher boiling point than the HCl. The HCl is still a gas as it gets cooler and cooler. Okay? Now, here's something that but Drew said that they're both polar. This is where we're going to learn that CCl4 is going to look like this though. So this is the one case where you're going to have phone call, but because it's symmetrical, it's going to actually still be nonpolar. But the fact is that you don't really have to say that. The fact that you can say, like Jack said, that because it condenses at a higher temperature, that means it's got stronger attractive forces. Because they said answer in terms of the information above, not in terms of the type of attractive forces. Because it condenses sooner, that means its attractive forces are stronger than HCl. Okay? But it's because it has the larger electron cloud and its LDFs are stronger than the combined LDFs and dipole-dipole of HCl. So they've asked that question a bunch of different ways about a small polar and a large nonpolar. All right, I have the study guide. Look at all of these questions, and by the way, I'm going to give you credit for classwork on all these. I'll show you. I'll look at that on Tuesday.
So we have a study guide?
It's on Google Classroom.
Is it you for a grade?
No, it's just very much a study guide. Know this, know that.
So only the questions we got in class we can do for
Yes, those two packets of AP questions.